brief introduction for the first 5 or 10 minutes. I'll also say a few things about what my colleagues work on, and then we'll have a discussion. By way of definition, the idea of particle physics is what is the world made of? In some sense, what are the fundamental constituents of the universe that we live in? And of course, it doesn't help just to have these fundamental constituents. You also need them to talk to each other so that you can have some forces and you can build stuff and so on. So that's sort of what would be a crude definition of particle physics. And of course, we've been very successful at this so far, right? We started from the 5 elements, but then you went down to elements that you see in chemistry. Then you have atoms, you break that down, you get protons and electrons, you break that down. And the idea is to find out, does this keep going, right? So we have a wonderful model. Since Sunil is here, I won't call it a theory because I've read his article. So we have a wonderful model which tries to describe all of the particles that we've seen so far and how they interact with each other. And this is one of the most successful theories across all of physics. Even within particle physics, it is tested over 8 orders of magnitude. And to have a single, so to speak, a single Lagrangian describe something over such a large range is kind of special. And wonderfully what has happened is no matter what experiments we manage to throw at it, it does really well in predicting the answers. And so that's great on one side. So typically what we are going to talk about, so a simple thing to keep in mind would be that the heaviest particles we've discovered so far are units of about 100 GeV. This translates to a distance scale of about 10 raised to minus 18, 10 raised to minus 19 meters. So we are sort of interested in what happens as you go down to those distance scales. Mathematically, you can sort of say that what we are going to do is there is some ultimate truth that describes the universe. So far, there is stuff that we know, and we are calling that the standard model, plus some additional stuff that may or may not exist. And we have reasons to believe why such a thing may exist. So there are many, many different problems, right? So clearly, if we have a theory that works over so many orders of magnitude, life should be good and we should be happy. The reason we are not happy is that, unfortunately, there are also certain phenomena that this theory doesn't incorporate. It doesn't explain all the answers. The glaring one is the thing in the center. So if we do a composition of our universe, we see that the kind of stuff that we see around us, so the so-called baryonic matter, is roughly about 5% of the universe. Roughly about 25% is dark matter, whatever that is, and the rest is dark energy. Even in the 5% of matter that we see, right, that, okay, at least I know about this 5%, even there are some really fundamental questions. If you look around in the universe, you see that there is an abundance of matter, and you don't really see large conglomerations of antimatter. Why is that? Why is there so much more matter when everything in the standard model so far to some extent tells us that there should be equal amounts of both? Now, that is not strictly true. We have found places where matter has slight preferences over antimatter, but certainly not enough to explain what we observe. The 25-27% of dark matter is another such thing. Clearly, there is enough evidence now for us to sort of, collectively as scientists believe that dark matter exists. What is it? Is it a particle? What kind of particle is it? What are its properties? We have ideas. Of course, we are not really sure. I particularly like this diagram. So Arun, I've seen this first in Arun's talk, I think. The make it, break it, or shake it, which is how you may go about discovering dark matter. So make it is obvious. In a lab, you collide things at high energy, you make dark matter. Maybe if you make enough, you can find it. Break it means, astrophysically speaking, there's dark matter out there. Maybe it collides and it breaks into stuff that you can observe. So that's nice. And the shake it is when a dark matter particle interacts with a standard model, say nucleus or something, and then there is scattering. So this is a very nice way of sort of also summarizing the various experiments that you do to do dark matter. Now this is meant to be an example, but if you stare at the standard model, if you're a theorist, you probably would stare at the Lagrangian. If you're an experimentalist, maybe at the particle content diagram, which is very popular, and I have successfully avoided showing it in a talk. So that's 1 point for me. If you stare at it, you will see questions that pop up into your head all the time. Why are there 3 families? Why are the masses the values that they have? And these values are wildly different. It's as if in this room, you had somebody who was sitting with a mass of 50 kilos, 70 kilos, and the neighbor next to you is like 3 tons. and you would not believe that you are the same species. But that's what we see here. So that is very surprising. There are also other deeper questions. Are there any fermions that don't feel the weak force? At the moment, all standard model fermions feel the weak force. There's no real reason. Some feel electromagnetic, some feel strong, but the weak force is shared by everybody. Why is there something deeper about it? There are other things that motivate what sort of aesthetic reasoning we want to do, and we're going to get into some of that during the discussion later. Theoretically and experimentally, how do we go about probing these questions? Sometimes, like that cartoon on the right shows that once I have a collider, every problem looks like a particle. It's an analogy to the carpenter who only has a hammer in his toolkit, so every problem looks like a nail. Now, it's not always obvious that each of the problems that exist in the standard model need to have a specifically collider or particle physics based solution. And so that is the challenge, that can we come up with the right sets of things? Are there tabletop experiments, for example, that can inform us about our universe? I'm now sort of going to switch and do a quick summary of each of my colleagues, and of course they will elaborate on their work later. So let me start with Deeptimoy. So at the moment, so of course these are interests that are spanning currently, right? People work on various things throughout their career. At the moment, one of the things that Deeptimoy will focus on for particle physics is something called an effective field theory. So if you look at the diagrams, the idea is that in a lab you can make beyond standard model physics, which is what that BSM is. You can make this beyond standard model physics if you have enough energy to make it. If you collide things at a high enough energy, you have enough energy, you can make beyond standard model physics. But if you don't have enough energy, what can you do? Turns out that you can use something that has been used in physics quite a lot. One sort of crude analogy could be if you think of friction, right? As a force, for particle physicists, friction you can explain in terms of the electromagnetic interactions between the different atoms. If you sit and decide to calculate that, of course, that's going to be maybe a lifelong thing and an insane idea. But nevertheless, friction as a description is very useful. It's an effective description at a sort of gross level of something that is happening deeper. More concretely here, what you can do is you can see manifestations of your higher energy physics at lower energy. And we've had this before in things like beta decay, where we could see the presence of a neutrino. Then you could go on to study muon decay and tau decay, and you could sort of figure out stuff about the W and how massive it was. So we've had examples in physics where we've done this before. The idea is that you take this higher energy stuff and you parameterize it in terms of some observables that exist among the stuff that you already know. So you have standard model particles, you can do a lot of measurements for them. Any sort of new contributions need to contribute to that. And so if you study this precisely enough, you are able to figure out all the effects that you're seeing, all the observables, do they come from the things that you already know, or are there some unknown contributions in there? So later on we will elaborate a little bit more on this. Let me quickly come to Arun. So at the moment, Arun's interests are slightly varied amongst different things, as you saw yesterday for both of them during the Astro and Cosmo panel as well. One of the things is this thing called traditional jet substructure. So as we will see a bit later, once I show you a little bit of the LHC and CMS, there are specific things that you observe in your detector that need to be correlated with what really happened. There needs to be, and we will talk about this during our panel, a considerable back and forth between theory and experiment to make sure that what you're observing, you can connect to reality. The other thing that has been going on quite a bit right now, and Arun has been telling me this since last summer maybe, and Rajesh actually sent me a paper, a lot of quantum information ideas are being started to apply to the LHC data. So there are obvious things like correlations between particles in terms of entanglement. I forgot the title of Rajesh's paper, what he sent. Did he send it to you?
I don't remember.
Okay, so there is a lot of this interesting stuff going on where you can use the large amounts of data that the LHC has to start to examine quantum information ideas in much more detail than you would have thought. So this is also something we will touch upon during our panel about this cross synergy that exists between different parts of physics. The last thing is kind of interesting. There are a lot of experiments that you can imagine doing that aren't collider based, that aren't also necessarily what I would call a high energy experiment, but these probe things at the very deepest level. So one of the reasons the standard model sort of has no description of gravity is that traditionally you sort of say that, look, the gravitational interaction between two protons is so small that you are not really able to study them in a lab. But now you can imagine tabletop experiments where, for example, you maybe throw not a single fundamental particle, but a collection of them under the influence of gravity, and you're able to try to study gravitational effects at that fundamental level, at the quantum level. So this was this last bullet. Okay, so that covers the two theorists. If you want to move to Seema and me, let me give a quick summary of what the LHC and CMS is. So Seema has been a member of CMS since its inception, very early, before the first data was taken, and I have joined in 2013. IISER Pune has been a member of CMS just as long, so since 2014, I guess, 2014, that's right. So the LHC, on the left hand side you see the LHC complex, is not just a single ring, but it consists of a bunch of different accelerators of different sizes. A lot of this is also meant to make our life a lot easier. CMS is the red circle there. So the LHC collides protons at 40 megahertz, which means 40 million times a second when it is operating, you have a collision. This means that so far we've had roughly 35 million billion collisions and counting. We are still collecting data. Now, the reason I say roughly is that that number is large enough that at this point, if it's 36, it doesn't really matter. It's a very, very large number. One of the benefits of having such a large number is that in principle, you have a large amount of data. So if you are creative and if you have a good idea and if you're smart about it, you may be able to extract a lot more from this data than what you would think. If I want to be very outreachy, what you can think of the CMS detector, it's like a giant camera. So the CMS detector captures the quantities of interest for each collision, and so then later you have access to every collision to do what you want. Of course, individual things, if you know some quantum mechanics, you will realize individual things are determined by probabilities. So typically what you study is you study ensembles. So these many, many collisions form an ensemble on which you can do a lot of studies. Now, specifically speaking, since we are experimentalists, one of the big challenges is to make sure that you understand your complicated equipment well. How many of you have cell phone cameras? Most of you. How many of you have DSLRs? Some of you have DSLRs. Do you know every function in the DSLR? Not really. But if you did, you would be able to use it a lot better. Now, imagine a detector that is insanely more complicated than your DSLR. One of the crucial things is just to try to understand what responses you get from the myriad of different particles that are going through it. So Seema has spent a considerable amount of effort in trying to understand the hadron calorimeter at CMS. This was in your PhD as well, and even later leading the group that actually does this. And today, we've come to a place where we can use like really modern techniques. So Alpana, who was one of our students, had a graph neural network. In fact, there is a poster outside that that is there where you can go look it up, where you use these really cutting edge techniques to solve really fundamental things about your detector. And you try to understand how it does. The proof is there in the results. You see that your resolutions improve quite a bit. Why this is good? This improvement directly translates into what you can say about physics. So in her work at the moment, Seema is focusing on two sorts of beyond standard model physics searches. Searches that explore exotic decays of the Higgs boson. While we found it, the Higgs is still relatively unknown compared to the other particles. I think Deeptima is also going to touch upon this a bit later. And also beyond standard model searches that leverage the fact that now you understand your detector really well. So what can you do with this understanding to target very specific things? The second thing is also out there in a poster by Vapi, I think. So please go check it out. And then that brings it to me. So the same thing I also do. So beyond standard model searches, for me, they involve leptons in the final state. One of the things that I also kind of think is important, and which we will also touch upon the panel, is this synergy between theorists and experimentalists requires results to go back and forth. The format of these results going back and forth is non-trivial. So you want to make sure that you can produce these results in a way that they can be used by somebody else right now and somebody else 5 years down the line. The last sort of block is actually common to not just Seema and me, but to even Arun to a large extent and other people in our field. Machine learning, the barrier to entry has gone down considerably, which means that now you can think of lots and lots of different applications at which you can throw this tool. So I've listed down some things. There are deep neural networks and graph neural networks and convolutional neural networks. There's encoders, there's generative models. Each of them finds a place that you can apply. So there'll be a couple of posters out there where you can go check this out. There are also additional exotic ideas that I think Arun will touch upon, that old fields of physics or mathematics, such as topology, how they come in here, given that you have a data set that is really large, how can you sort of go about addressing that? So I'm going to stop here. Now what we're going to do is maybe we'll do a quick round where people can, my panel members will tell us what sort of motivating them right now. And then we'll sort of devolve into a set of questions that we agreed on, and we'll have a discussion there. Feel free to jump in at some point if you have a strong opinion about something. Okay? So should we start with you, Deepti? So I'll repeat the question quickly. So the question is about that since you have such a large number of particles going around, presumably, that's like a condensed matter system. It's like a collective system rather than the reductive individual particles that we talk about in particle physics. Maybe that is my mistake. So an individual collision is between two particles, and maybe of order 500 interesting things come out. But these all are ultra relativistic in the sense that they interact with the detector faster than they can interact with each other. So in that sense, the detector interacts with each individual particle, and that's still why we can do reductionism. The 35 million billion collisions is an estimate of how many such collisions you did. So that's like how many pictures I have in my stack, but each picture I'm going to analyze individually.
Yeah, so I'll just take a few minutes to tell you my view about what the big questions and contemporary questions in particle physics are. So I think the big question is to now try to find out where the next scale of new physics is. Now, this is a difficult task and also a very uncertain task for experimentalists, because we don't know we don't have any idea about where the new scale is. We just keep increasing energy and try to find out where the new scale is. Now, more specifically, we don't know where the scale of neutrino mass is, which in my opinion is a very important scientific question. And to know whether the neutrino mass is of a particular nature called a Majorana mass. As of now, we have not seen any excitation of our Lorentz invariant, Poincare invariant vacuum which has this property. Because I use this technical language because you'll see Majorana states in quantum matter physics, but they are not excitation of the Poincare invariant vacuum which I'm talking about. So we haven't seen any excitations of the Poincare invariant vacuum which is Majorana-like. So that's a very important scientific question. Another example is to understand where the scale of breaking of some approximate and accidental symmetries of standard models. Say, for example, baryon number. This is an accidental symmetry and a very good approximate symmetry of standard model. And I think it's a very fundamental question to know whether this is really at what scale this breaks down, and where we would expect to see protons, at what scale we would expect to see protons to decay. Now, these are, I think, in my opinion, grand questions which we don't know the answers of, and would really like to know the answers to these questions. Now, more urgent questions are, which I call contemporary questions, are questions about Higgs, for example. Now, there is I think, misconception among a lot of people that just the discovery of Higgs means, it's kind of is the end of it. We don't have to, then we kind of know everything about standard model. We don't have to worry about anything else. But that's absolutely not true. At least scientifically, that's absolutely not true. Now, in fact, what I think that Higgs represents a groundbreaking advancement in physics, and the fact that it is the simplest elementary particle makes it profoundly enigmatic. Now, why? Because we have not seen any particle like Higgs before. I'll elaborate on it. And the fact that LHC has seen only Higgs boson and nothing else makes it extremely interesting. Now, for Seema and Saurav, in my opinion, the strategy should be put Higgs under the microscope and study to death, and I think only then we'll know, the true nature of Higgs. So the other slide is here. Yeah. Now, let me, in just 2 minutes, let me just tell you why we have not seen, I said we have not seen anything like Higgs before. First, we have never seen a point-like scalar. Now, for that, first I have to tell you what I mean by point-like scalar. Because sometimes we say fundamental particle, but this fundamental particle, this whole idea is not very fundamental. Because, if you say that if a particle is fundamental, you have to tell you that at what scale it looks fundamental. If you send a probe, if you send a photon with certain wavelength, with respect to that wavelength, it might look fundamental, but it may not look fundamental if you send a photon with a much higher frequency. So now we have seen scalar particles. We have seen pions, for example. But if you remember, the pion mass is 100 MeV, and pion was really fundamental at the scale of inverse of its mass. This is roughly the Compton wavelength of that particle. I think this is a very good way to ask this question, that whether a particle looks point-like. You can ask whether the scale of its inverse mass, it really looks point-like. Now, pion did look point-like at 100 MeV inverse scale, but it did not look point-like if you increase the energy scale by 5 times. So, at around 500 MeV inverse, it started showing structure. Now, for proton is completely the other way around. Proton looks terribly composite at the scale of its mass. At inverse GeV, it looks terribly composite. Now, for Higgs, what is the status? The Higgs mass is roughly 100 GeV, but even at TeV scale, it looks point-like. So, it looks more point-like than pion, definitely. Not much though, only slightly more point-like than pion, but we still don't know whether it's really point-like. And I think it's important to experimentally find out whether it's really point-like and so, because we have never seen such a thing before. And my last point is to ask whether Higgs, so as of now I was thinking about whether Higgs look point-like to external probes. You send a photon and whether Higgs looks point-like. But then for Higgs, you can ask whether it looks point-like to itself. Because Higgs, among all the elementary particles, Higgs is the second one which has self-interaction, other than graviton. Now, some of the experts might say that, color, the spin 1 gauge bosons, they also self-interact. They don't, they need color. Graviton, in Einstein's gravity, also does not self-interact, but in higher derivative gravity, they can self-interact, but which we will never measure. So, Higgs practically is the only particle in the world which can interact with itself, which can have a 3-point vertex. And so that's why it's very important whether this interaction exists. In standard model, it does exist, but we haven't experimentally probed whether this exists. So this question is also not answered. So that's why Higgs is incredibly interesting, and I think there are a lot of things one can try to understand about Higgs, and the Higgs physics, or trying to understand details about Higgs is an open question, and I think Seema and Saurav and the rest in the community, they should really, put in effort to try to understand it. My last sentence, that for this, you actually need a new collider. LHC will actually not do it. So this is a very strong physics case to have a new collider. Whether you want to spend this money on this or cancer research, that's a different question.
I don't agree that it's an either or. I don't think it's a collider or cancer research. I think it's both. So I'd like to now sort of pose certain questions to my colleagues with their slide up. So Arun, one of the things is, please tell us a bit more about your work, but also I'd like you to maybe touch up upon how higher ideas in sort of high energy physics, that is higher energy than collider, sort of feeds down into ideas that we would have here or into your own work.
Yeah, so I'll kind of interpret that in a slightly broader way. I won't take that long. So one thing I wanted to emphasize is, this nice synergy between various fields. Each of us may choose to do condensed matter physics, formal theory, etc. And some of the points I would like to touch on today, and which was touched on yesterday by panel members in the astrophysics cosmology. So there's a lot of cross-pollination between the fields. So for instance, this first topic which Saurav, me, along with some very smart students. So there's Saurav there, he's from CDAC. I see Ria at the back, and there's Shreyas there. So there was this old idea of jet substructure. Loosely speaking, what it said is, there are these particles called gluons, which form jets. There are also quarks, which form jets. So naively, they look the same. But is there a way you can go inside these jets and try and distinguish them? So this is a traditional idea which came back, which was, which gave us a lot of leverage in trying to, find the Higgs boson in certain channels, try to search for BSM, beyond standard model physics, etc. So one of the things which recently has garnered a lot of interest is, as Saurabh alluded to, is to use very, what might be thought of as naively formal differential geometry, ideas from topology, to actually do, very, very important and crucial distinction. So kind of marrying traditional jet substructure techniques along with things like homology, persistent homology, for example.
Arun, can I just probe that a bit? So, for example, how would you go about discovering these detailed mathematical techniques? So, for example, I don't read math papers.
Yeah, I should also say, when I was a graduate student, all the different geometry I learned is from Sunil's nice book, which is a lecture note from SCRC school. So the basic idea is, if there is a, you have a sphere, think of it like a data set which has the shape of a sphere. There's also a data set which looks like a donut, a torus. Now, you know that loops on a sphere can kind of be shrunk to a point, but on the donut, you have kind of two complementary loops you can draw. So one can use similar ideas here. So the idea is there is some multidimensional space with some data, and we want to kind of understand the shape of this data. So this is something which we have starting to explore along with a lot of our collaborators. So that's one thing. So the second thing, as again Saurabh summarized, many ideas coming from quantum information, which I think many of our condensed matter colleagues and also from formal side, people like Sachin, there's again a lot of interest in applying, things which as particle physics we interpreted as symmetries or certain bounds. What does it look like from a quantum information perspective? So many times in various fields, and definitely in particle physics, when ideas are taken from another field and you try to think of problems in particle physics from that perspective, it has very often times led to spectacular insights. So even what we now call the Higgs mechanism or spontaneous symmetry breaking, it's hard to pinpoint. There were condensed matter physicists like Anderson who had similar ideas. So this is a very, so there is a similar evolution happening with quantum information. Things like entanglement, thinking of entanglement entropy, things like complexity, which for a quantum computing person will mean something, but there are these interesting questions you can ask, even from the particle physics side. And the last thing, one of my interests along with my students has been on understanding strong field quantum field theory. So there are things which are, believe it or not, still not understood after 90 years. So there are things which were calculated in 1950, but just because they are not necessarily considered very fashionable these days, nobody has bothered to calculate them, but which are still very relevant. So there are these extremely strong lasers called X-ray free electron lasers, which are there in many parts of the world. We don't have one yet, as far as I know, but there are things you can do with these X-ray free electron lasers to probe fundamental physics which we cannot do otherwise. Specifically things like light degrees of freedom, like axions, milli-charge particles, etc. And again, this is, ideas coming from the formal mathematical physics side, things like what are called resurgence. If you just have few terms in a perturbative series, can I still reconstruct the full master function? And many times the answer is yes. And things like a divergent series are actually sometimes more useful than a convergent series. So there are very interesting theoretical problems here, and I'll kind of stop.
Thanks, Arun. So Seema, I am going to sort of take the liberty of just diving right into the deepest question that we sort of talked about. So you've had a career where you started on CMS 10 years before the Higgs was discovered, and now it's been more than 10 years after. One of the things that very importantly we touched upon the other day was de-emphasizing like the super large ideas and also thinking at the same time about what students do or what we do in terms of incremental progress. Could you say a few things about this?
So let me first start with like what I am doing and what motivated that. So let me get back to like from Deeptima and Arun and get back to something, a broader picture again, is that what are we doing? And if you want to connect to like what was discussed yesterday in Astro and Cosmo panel, you started with Big Bang kind of thing, right? So what are we trying to do at LHC? We are sort of trying to create those conditions that we can see what are the elementary particles which were there. So when we say point-like particles, essentially we're talking about elementary particles, and the definition becomes there is no internal structure to them. So for the electron, you cannot talk about any internal structure. Okay, and what we want to understand about these particles, how they interacted with each other. So what are the fundamental interactions which led to the universe the way we see it today? Okay, so all those details have to come in. So what we are looking at really the particle nature of the whole thing. But the broader game, like broader, all of us like aiming towards the same question that where it all came from. So that is the starting point for us. That's what we are doing at the LHC. Now, when I started with like sort of my research career as starting with a PhD student, the dark matter is still sort of elusive and interesting. And we have no clue about what its particle nature is. So my theme, like sort of, if I really follow the theme of my research that has been towards like looking for the dark matter kind of particles. So basically these are the particles which will not leave any signature in the detector. They will just fly away. And then how do you infer it? That's what we call the missing momentum, the energy being carried by them that is completely missed out. So if you see my sort of like posters or the papers, this missing transverse energy comes out again and again. So that's the theme we have been following. In the recent times, as Deeptima also mentioned that the Higgs boson is sort of established, that we have a new scalar particle. Now this is a probe for the new physics for us. And that's what I'm moving towards now. And that's where we are trying to look for these axion-like particles in the decays of the Higgs. So these are the rare decays of the Higgs bosons. And these also again relate to some of the astroparticle interest and the dark matter and things like that. But to be able to understand all this, like missing energy, you have to understand your detector very well. And that's where my interest in the calorimeter detectors started. So calorimeter traditionally looks like measuring the heat, but then it's not the thermometer we are putting in. We are just trying to get the electronic signature out of it or some scintillation signature out of it. So that is the broad idea which we have been following. Now, LHC, okay, fine. We are running like since when first data came out in 2010. And now we are already preparing for the high luminosity LHC operations, which is supposed to start end of this decade. Right? So most of like my previous 2 students out of the 3, they have been working on like getting these calorimeters ready for this detector. Okay? Now coming to the discovery part of it. So I first came across the Higgs mechanism or the spontaneous symmetry breaking in my master's when I was doing HEP, one of my elective courses. And the actual discovery which happened was in 2012. That's when we announced it. So it was really an experience being at CERN and really seeing those equations getting materialized. That was a fantastic experience. But then what? When I first came across the Higgs, as me, like as a student, it was back in like 2000 or so. And it took more than a decade to like sort of see it, okay, fine, it exists. And that's the case when people have been working on it for previously 20 years. The ideas of the Higgs, supersymmetry and all these are like sort of since like half a century now. So now what next? That becomes the question, right? But then you need to have patience. So it's not that we don't care for discoveries? Of course we care, because otherwise the field is stagnant. Which direction to go for? Right? There is no fundamental theory which tells you that, okay, fine, this is the particle you should look for, this is the mass. We try to infer from what our observations are. We constrain what phase space or what parameter space you want to look at. So just saying that if I don't have a discovery in my PhD career or 10 years of my faculty career, that sort of is not a loss. You are preparing for the discoveries which are going to be upcoming. I mean, I will call my career a successful career if one of the students, they are really sort of instrumental in making some new discovery 10 years from now. So that's what my take on this part will be, that you're not going to get discoveries every second week, second year. It takes time. And these kind of experiments, they have the long time schedule. I think the LSC first ideas came up in 1984, 85, something like that. And the CMS, the first technical design report, or actually it was the letter of intent, came up in 1995. So here we are today with respect to as far as the LSC is concerned. And that time, I think the lab even not even started, or it was just middle of it when the LSC ideas started coming in. So we just keep moving. The limitation becomes that how far can we go, but then it also, the technology which comes in, that plays the big role. So tomorrow, if we have the high magnets available, fine, there will be a sort of breakthrough, and the whole scenario will change. If there is a discovery from the neutrino sector, or from the gravitational sector, or from some astroparticle experiment, of course scenario will change. So the good thing, I mean, the interesting thing for me for this field is that it connects to so many various pieces. There are experiments where we are looking for what nature tells us, that is for example, the cosmic experiments, astro experiments, and here we are trying to really tinker the nature at the LHC and trying to see that what nature is telling us. That's the basic idea.
I think that's a really good segue. So Arun, we've also touched upon this. What is this feedback that happens across different fields from particle physics? I mean, there is certainly the experimental side. Please, you can say a couple of things about that. But I'd also like to hear about the theory side of things. Ideas here generating stuff elsewhere, and ideas generated elsewhere feeding back into the field.
Yeah, so I'm definitely not an expert on to comment on the broad answer to what Saurabh is asking. But personally, for me, like, things like, so I cut my teeth on things like supersymmetry, QCD, jet substructure, collider physics. And in the last few years, I've been interested in astrophysics because I realized that, for example, there are systems in astrophysics like neutron stars, the local environments near black holes, etc., which provide exquisite and scenario to test things which otherwise we can't. So it's, as Seema is saying, like there's a complementarity. Like collider physics, we can do something, so they're not competitors. They're like, complementary to each other. So astrophysics is, for example, one thing which I've been trying to, learn more about, specifically things related to astrophysical compact objects. So in my personal journey, learning things about neutron stars, what is a magnetar, realizing that you can do strong field or test, calculate, observe strong field effects. So like, so we all learn Maxwell's equations are linear, right? And people who are working in optics and who are more experts than me, they'll also tell you that, no, if you have certain nonlinear material, there's something called nonlinear optics, etc. But the fact is, surprisingly, that even in vacuum, if you look at the full theory, let me call it generalized Maxwell's equation, they're not linear. There are corrections to what we think of as Maxwell's equations in the full theory, which is called quantum electrodynamics. So you have light by light scattering. You can have rotation of polarization of light even if it goes through. So there is again another cross-pollination. So people like, Pavan, Professor GRK in TIFR, who work with very high intensity lasers. So there is kind of a cross-pollination. So that's another thing I would say. So, and as I mentioned, even from the what might be categorized as more of a mathematical physics or formal theory, there are many ideas which it's not even speculative. It's like at the level of things like engineering problems. Like there is a very clear way to use things like topological data analysis to make non-trivial interpretations.
Yeah, I can comment a little bit more on the crosstalk with the other fields also. So at the LHC, one of the issues which we face for the detector part is the radiation hardness. There's a lot of particles coming in, coming out, and even in your UG labs, you know it, right? That how much protection you have to have for your radioactive sources, which are just like very minimal activity. So for the HLLHC, one of the challenges has been to really come up with detectors which are really, really radiation hard, and in that direction, essentially so far we have been using is one of the silicon-based ones. Those are really sort of. But all these techniques which we are using for the machine learning and all, they have existed for the ages. I mean, there is no something new about it. It's really the ingenuity lies in the algorithms which have been developed and the available of the computational power. But at the same time, we are also getting our detectors which are more and more granular. That means what we are talking about here, 100 million channels, at LHC we will have something like several hundred millions of them. So that provides you a lot of information in terms of like the high granularity calorimeter, which I was working with my students, is essentially 5D information. You have X, Y, Z time, but at the energy. So you can really go in the details of it and try to figure it out. But at the same time, a lot of interest is again coming back to the tabletop experiments. So one of the things which we are trying to sort of explore is, so for example, if you say E plus E minus bound system, positronium, and if you can get new physics searches in that direction, some very low mass particles like the pseudoscalars or axion-like particles. But for that, we have to come back to our colleagues and ask about, like, for example, what are the sensitive detectors we can use? If you want to break an electron-held pair in the silicon, you will have a few electron volt required. But if you want to go for a superconducting nanowire, probably a much smaller a few, like fraction of the electron volt which will be required. So there, the crosstalk essentially starts really on the detector part of it. And for the experiments, you can have a lot of data, but you need your instruments to create the data and measure it and record it, right? So the crosstalk in that sense in particle physics is both the sides, both theory as well as the experiments and the other fields. So that's one thing which I just wanted to add.
So, Deepti, yeah, you add to that and then we'll go to audience questions.
So I just wanted to add, to this end. Say, for example, the first evidence of physics beyond the traditional standard model came from astrophysics experiment. It came from looking at neutrinos from sun. So from solar neutrino experiment. And this told us about the existence of massive neutrinos. Now, even today, the strongest constraints on with some combination of masses of neutrinos, as Orko mentioned in his presentation, comes from cosmological observations, not from terrestrial experiments. So you see that these fields, astrophysics, cosmology, and also particle physics, they are quite linked, and information from one field can often tell us about other fields and vice versa.
This is our version of the multi-messenger idea.
Yeah. So in particular, early universe cosmology, there you'd like to know about new heavy states, which you cannot probe at LHC because we don't have enough energy. But we can kind of think of the early universe because of extremely high temperature as a collider, as a cosmological collider, and generate a lot of heavy particles. So the kind of questions we often ask, they're cross-disciplinary, and experiments and observations from one field often gives information about other fields also. And then just last thing, also for dark matter searches, in particular for very light dark matter searches, which has been quite fashionable in the last 5 to 10 years, you need material with extremely low threshold. Materials like Dirac material, single photon detectors, these has been talked about quite a lot in the high energy physics community for search of very light dark matter. And here also you see a lot of crosstalk between, in particular, experimental condensed matter physics and people who are interested in dark matter searches. This unfortunately is not happening much in India, but in the US, I think this collaboration is quite strong.
So we'll open it up
We are starting on
questions.
that.
Yeah.
Thanks for the overview. In fact, yesterday I could not also ask a few questions related to the astro thing, and it is probably connected to these concepts. Since you also mentioned about the dark matter detection issue, which I think, in my opinion, is one of the outstanding challenges in physics today, there is also a very deep connection to levitation optomechanics, which is an area which is emerging, where you essentially isolate a particle of interest in vacuum and look at tiny fluctuations, which is as much as few kind of hertz, which is extracted. A lot of things actually build upon the techniques which are built on atom cooling, trapping, optical tweezers, and other things. So one of the issues here in this particular thing is, and also connected to some of the questions what people were interested in, is to look at candidates for this dark matter. In fact, Shaurik was also actually having a very nice elaborate discussion with Diptimoy. How should we really think about this problem? I know detection is a major challenge. Because of the fact that it is not amenable to electromagnetic kind of exploration, our understanding is probably severely lacking in this whole framework. It is as much as 90% of stuff we actually are not able to observe happens to be outside this realm. It is actually it's astounding that we still don't understand. But I think particle physics may have some clues over that. Where should we really start approaching this problem? If you folks, including the astro folks, can elaborate a little bit, it'll be very interesting.
So, if I may, Pawan, so you mentioned about these suspended levitating. So, in fact, see, although we generally say dark matter should not have any interaction, like for example, if the interaction, like even an electromagnetic interaction, is very weak. So there's one candidate called fractionally charged or milli-charged particle, but it's not milli, it's like 10 power minus 16 times the electron charge. So people have been trying to use suspended, basically a generalization of Millikan's oil drop experiment to actually see whether, so at some point I was also asking Bhaas, where like things like in a penning trap or in some of the ion collision experiments, like if there is a flea on an elephant, to make an analogy, where the flea is like the milli-charged particle and the ion is like the elephant, by looking at subtle deviations in their dynamics, can we put limits on? So people have actually looked at things like that. So I just wanted to mention this specific thing since you mentioned.
So I think that's one of the major challenges, is that there's no natural direction to look for in terms of what kind of particle can be dark matter. So if you look at the reviews that have come out recently, dark matter, or what we call dark matter, can span a mass range of 90 orders of magnitude. From primordial black holes on one side to things like ultra-light dark matter, which is like 10 to the minus 22 electron volts. So right now, I think the best strategy is to develop as many tools and probes as possible. So people were pointing out the complementarity in terms of techniques. They also do, quite fortunately, also lead to complementarity in terms of what sorts of models you can probe. So the models you can probe with, say, direct detection are different from the models you can probe with indirect detection versus cosmological signatures. So that is just the state of the game right now. But things like this, even if, whether it's through milli-charged dark matter or any other interactions, these types of experiments, I think, are quite promising. So, yeah.
So this has been a very illuminating session about how high energy physics is done and what are the connections and what are the goals. But I think one thing I was hoping to see, and I hope you can tell me, is what is the discovery status today of the two main projects for which LHC was founded, which is, I believe, is supersymmetry, well, apart from Higgs, of course, which we have heard about, supersymmetry and extra dimensions. And I just want to say before you answer that, it's very important to have a real answer from real experts, because social media is always like one way or the other way and very extreme. I think it would be lovely to have a clear, balanced answer where we are today. Thank you.
I'll add some sociological stuff a bit later, but yes, please. The Suzy answer is you.
So when the LHC started, the expectation was Suzy's round the corner, but their corner came out to be that of a circle. So you can see what happened. Now, for the current status. So far we have not seen anything which is concretely to be said that, okay, it is beyond a standard model. Okay, once we see some new signature, and then we have to start characterizing it, whether it's supersymmetry or is something else. That sort of comes the second step. We have not yet we are stuck with right now that it's frustrating that you have a lot of data, but still nothing has come out yet. However, saying this thing that, okay, fine, the Suzy is dead, or any particular scenario is dead, is not correct either. We know that a standard model is really, really sort of successful theory, a model, but it's incomplete. We know it very well by now. Okay, so there's something which we are expecting to happen. However, keep in mind that so far we have hardly collected like few % of the overall LSC program, what the data it's supposed to give. 90% of the data is still to be collected at the HLLHC. So we have like more than a decade to look forward to. So that would be what I would like to say, that we have not yet done what needs to be done fully. We are just waiting for it.
So wait. So let me add one thing to that. So my thesis was a search for supersymmetry, and I think initially this may be true of SEAM also. We started off with the paradigm that you're going to look for these particles and they will show up as like a resonance or clear distinctions. Now even within CMS, the subgroup that searches for Suzy is no longer called Suzy. It's called new physics searches. I think collectively a lot of experimentalists are now moving towards a mode where you wouldn't look for something specifically, but rather look for deviations. But I also in some sense feel that if Suzy is not like a glaring, 1 TV gluino or something, it's going to show up as a general disconnect across several different things rather than in one place. So it is in some sense nice that we need to do this, that a real 2 sigma thing here and a 3 sigma thing there, which we wouldn't usually put together, we would need to do some of these things. So yeah, and of course I agree with her that it's anyway way too soon to say some of these things.
So can I just I just answer to Sunil's question?
Extra dimensions, or
no,
we didn't
about
answer
supersymmetry.
that,
Because there's also the audience is general. So let's say that you have a charge distribution, and then you want to see whether the charge distribution has monopole, dipole, and what kind of multipole moments. So first you basically see how the electric field varies, you fit and you find out that there's monopole and then dipole, and then you see that, okay, I'm not seeing the quadrupole. And then can you say that the quadrupole moment is 0? You cannot. Because what you will see is you can only say that based on your fit and the experimental precision, you'll say that it seems that the quadrupole moment is small. Compared to its effect on the electric field of the potential is small, compared to monopole, dipole, and so on. So you'll give a bound. So in the same way, what LHC has done is to prove that these supersymmetric particles are not below roughly a scale which is TV. I mean, it could be 1 TV, 2 TV, depending on details. But whether they are there at 3 TV, 4 TV, 5 TV, that we don't know about. And nothing.
Are they really ruled out below 1 TV or?
No, you can always, find holes where they are not ruled out. But I'm saying that typically, roughly, let's say TV or so, it depends on whether you are talking about colored particle or not colored particle and so on. But let's say few hundred GeV to TV.
But I'd go beyond. I wouldn't say it's also that we are not nitpicking when they say that they are not ruled out. There may be broad sort of strokes where you say they are not ruled out.
So we can discover them tomorrow or in a different collider. So scientifically, I think not much have changed other than this fact that these states are above roughly a TV or so. Now, as far as the motivations for low energy supersymmetry is concerned, all of them are still intact. And a supersymmetric particle below TV or above TOV will not make much of a difference as far as things like grand unification is concerned and so on. So I think the game is still open, and many of the statements which you see in see, in public, I think they're just scientifically wrong.
So just to add one comment, which goes back to, I completely agree with Seema. I think before LHC, there was a, apologies, I'm being recorded. So there was too much hype on supersymmetry, but unfortunately after LHC, what happened is it went in the other direction. And I completely agree with Seema that both these are wrong. The only thing I want to add is, see, some of the initial raison d'etre for supersymmetry, that, oh, there is a UV, what we would call ultraviolet sensitivity to the Higgs mass. So for us, low energy supersymmetry was going to solve this. And since we have not found colored particles below a TeV, that dream has been dampened quite a lot. So I'll slightly disagree with Deeptimai, but also agree with him and also agree with Seema. So this is the only footnote I wanted to say. And this is the reason for a lot of the illogical pessimism in the field.
So, if you really think it this way, the Higgs boson is discovered and a lot of properties have been established. They are consistent with the standard model. But we also know that the framework of the standard model, if you try to calculate the quantum corrections to the mass terms and all, they become sort of divergent. Now, to me, that's sort of the most urgent problem to solve, that there is something more going on. Because you have a particle here which is expected, which beautifully sort of really is consistent with what we are expecting from standard model, but at the same time, we don't know anything about it. So if you ask me, like, my motivation, dark matter and Higgs, that's where it comes from, essentially my interest and my theme of research, that what I would like to sort of address as soon as possible.
Yeah, we'll encourage students to ask the question. Yeah. We'll come to Shovik surely. Specific questions from students?
Among the millennium problems, there is one relating to the Yang-Mill existence and mass gap. And what I understood is this as having some relation to that. So to what extent, I mean, what light can you throw on it? Yeah?
None of us directly work on it. So just to elaborate, so there is this, millennium problem which says, does pure Yang-Mills theory have a mass gap? Or to put it in crude terms, there are these massless particles which come up in strong interactions, strong nuclear force, called gluons. Can they form, roughly speaking, some kind of bound state, like glue balls? So that's, must they, as Sunil correctly says. This is the problem he's referring to. One comment I'll make, I don't work on it, but see, many times in physics, across a field, usually if there is a small parameter, we can do perturbations. We can, systematically calculate corrections. This is called a perturbator. So most problems in quantum chromodynamics, unlike quantum electrodynamics, which is the quantum field theory which generalizes electrodynamics, these are non-perturbative. Like, you don't have a good handle on, so this problem, that's why it's very difficult, that you don't, and the techniques available to us to do non-perturbative physics and definitely non-perturbative quantum field theory is very limited. So one of the reasons, like for example, supersymmetry, as a toy model for QCD, there's something called supersymmetric QCD. It's a toy model, but it has many of the features of the QCD of our universe. It gives us theoretical understanding of problems like this. So Sunil can correct me, but so in certain theories which almost look like QCD, but these are mathematical theories, we have been able to, in quotes, prove that things like confinement and the problem you're referring to might be there. But otherwise, this problem is still open.
Hi. So yesterday we heard from the atomic and molecular physics panel that we are getting better and better at measuring time, attoseconds and all that. And we're also getting better at measuring shorter distances. And here to probe new physics, as Deeptima also was saying, we want to go to higher energies, build a better collider to, for instance, measure self-interaction of the Higgs and so on. How correlated are these two developments? Is it possible that we'll get new physics from more precise measurements of time and distance rather than just going to higher energies as well? So I just wanted to get your opinion on this.
So I'll try to give a short answer and we can have a longer discussion later. 26% is dark matter and 5% is usual baryonic dark matter. That 5% is extremely complicated in terms of what features it has. There's no reason to believe that each of these things is not going to produce new physics, which is different from each other. Like, they're not all necessarily going to maybe discover the same effects, But being able to study physics at attosecond will discover some effects. Going to higher energies will discover something else. So that's how I'd look at it.
Do they complement each other, these two studies?
Sometimes they do, but the complementarity will be model dependent, right?
Hmm.
It depends on if.
High energy is definitely one frontier. But as Seema, Saurabh will also attest to, see, Higgs factories are going to be in few hundred GeVs. Now you will think, we have a machine which is running at 14 TeV, and are we demoting? No. So there is also a precision frontier. Because, so just to give you a funny story, back in the day when hadron colliders, which are complicated objects, because a proton has some structure, people proposed hadron colliders. There were like very eminent physicists who said, we can never do physics by throwing chairs at each other. They're saying it's too messy. How are you going to, we should have E plus E minus all. So there is also precision frontier. So the Higgs factories, like what Seema was alluding to, precision, they will help us. They're at a lower energy, but will help us do very precise measurement of Higgs-Yukawa coupling and things like that. So I just want to, and then there are other frontiers, but I just wanted to add this.
There's one famous example of this, which I think you know about. This is the G-2 of either muon or electron. You see, there we are not actually doing experiment at high energies. We are just trying to measure the gyromagnetic ratio of electron or muon, for example, more and more precisely. And by measuring more and more precisely, we are trying to understand whether there are new physics at very high energies. Because if there are new physics states at very high energies, at higher orders in perturbation theory, as you all know in quantum mechanics, if you want to compute a correction to the ground state energy, in higher order in perturbation theory, all states contribute, right? So you are sensitive to all states of all high energies. But for that you need precision. So.
Yeah. So my question is very rudimentary and experimental. When I see these detectors that being used in these particle accelerators, the final detectors are at least, or most of them actually work on the principle of electromagnetic interaction. So is it given that whatever particle physics problems of strong interaction, weak interactions that you are trying to study, all of them will kind of come down to final electromagnetic interactions that you will be able to measure it? Meaning, are there any detectors which work on the principle of strong interaction or weak interaction? And
yes, so you do have detectors where you will have more nuclear interactions, which tend to be strong interactions. Seema is the world's expert here sitting. But aside from that also, a different way we would put it is that you detect particles by the most common thing that they do. So the initial interaction will be the strong or whatever. Ultimately, it devolves into trying to generate visible light at some sense, because that's easy. So then the subsequent interactions may not necessarily be strong. So it will be a mixed thing that sort of goes on. I mean, Seema can elaborate, but yeah.
Yeah, we'll take a last question. A student question is there. So we can take the discussion outside. Yeah, please.
Hello, sir. Like recently I read one of the article by Penn State and University of Columbia. Like they are claiming that there is one of the particle which is moving in one direction, it has a mass. But when it is moving in the other direction or a perpendicular direction, it is like massless particle, and they name them as a semi-Dirac fermions or like a quasi-particles. So what's the actual mechanism behind those particles? Like they are acting like a massless particle or
This
have
is a
a
question
mass?
for Srijit maybe. It's not a particle physics question, but rather a different panel question.
Okay.
But
We'll
Srijit
get a
wants
quick
to,
comment because Srijit is going to make appearances in two panels later. And
So then re-ask the question then.
They are not they are not fundamental particles. They are some emergent excitations, presumably some kind of fracton that appears in a many-body system.
So you know what phonons are, for example? Have you heard this term?
Yeah. So
It's not a
these-
real particle, right? It's that sense. It's an emergent property that behaves like a particle, and so you describe it.
So the terminologies are borrowed from the particle physics
Right.
names of the particles that way.
So just to say, like as Deeptima was saying, we have Majorana particles, which are like something fundamental, which has a particular meaning in terms of charge conjugation. But in condensed matter physics also, there are Majorana excitations. It has certain properties which are similar to what we are talking about, but they are actually fundamentally different.
Okay,
so
the very last one. The very last one.
So fresher here. So I have been studying about per se very the general relativity and the particle physics, and I have been hearing this term topology, differential geometry, and source spaces, Banach spaces, and all of the very different things. So my question is, can this be the actual bridge between this, the grand unification and all? And do we really have like tools to even theorize the grand unification, or can we just rely on mathematics?
So that's a very good question. So we definitely have tools. So the way I think about it is that, see, mathematics gives us consistency conditions, okay? But that is important, because if you're writing some theory which has, some inconsistency, anomalies, but then, nature is a final arbiter. If you're saying I want to describe something in the universe, nature, we have to look at experiments, observations, etc. So we have tools. So things like grand unification, where we think that maybe all three forces unify into some, larger, this is something we are looking for. We have put limits. There are limits coming from things like measurement of proton decay. Okay, so we have been able to put constraints on what kind of grand unified theories are possible, etc. So the answer is yes, there are tools where both mathematics as what theory as well as experiments go together. But if you're interested in I want to understand the mathematical structure of a theory, that is also a worthy endeavor. Okay, I want to write a toy quantum field theory because I can't calculate certain things in a more realistic quantum field theory, but let me try to get some theoretical intuition or understand. And things like new mathematical structures have many times arisen from, so you might have heard of the Dirac delta function, right?
Yeah, I do.
The first time Dirac wrote it, he didn't, it gave mathematicians, okay. But he just wrote it. Now there is a theory called distribution. So there are more generalizations of this. And Sunil is an expert on many of the things like modular forms, mock modular forms. So there is a very nice, as long as each of us is being honest about what we are doing, that is fine. We should do what we love.
Okay, we'll take the question outside. If you